The planet closest to the Sun should be one of the hottest and most hostile places in the solar system. Yet Mercury hides something that seems almost impossible: enormous deposits of water ice. Not a few frozen patches, but potentially hundreds of billions of tons of ice locked inside permanently shadowed craters near its poles. Mercury's surface can reach around 430 degrees Celsius during the day. It has virtually no atmosphere, no oceans, and no rain. And still, in places sunlight has never reached, temperatures can fall low enough for water ice to survive for billions of years. The mystery becomes even stranger when you realize that Mercury is not simply a scorched rock. It has a giant iron core, an unexpectedly active magnetic field, a constantly changing exosphere, and a tail of sodium stretching millions of miles behind it. So how can ice survive on the planet closest to the Sun? The answer is surprisingly simple. Mercury has almost no atmosphere to move heat around. On Earth, air and weather distribute heat across the surface. Mercury has nothing comparable. A crater floor that never receives sunlight can remain incredibly cold even while the surrounding landscape is being blasted by intense solar radiation. NASA's Messenger spacecraft provided some of the strongest evidence for polar water ice. Radar observations and neutron measurements showed signatures consistent with ice buried inside permanently shadowed regions. But that creates another mystery. Where did the water come from? One possibility is that asteroids and comets delivered some of it over billions of years. Another possibility is even more fascinating. Mercury may actually produce water through surface chemistry. The solar wind constantly bombards Mercury with protons. Those particles can interact with oxygen-bearing minerals and hydroxyl groups in the soil, creating conditions that can produce water molecules. Much of that water is quickly destroyed or lost to space, but some molecules may migrate toward the cold polar regions and become trapped inside permanently shadowed craters. In other words, the Sun may indirectly help create some of the water that eventually becomes frozen at Mercury's poles. But the ice is only the beginning. Mercury has one of the largest metallic cores relative to its overall size in the solar system. Its core accounts for roughly 3/4 of the planet's mass and dominates its interior. That raises a huge question. Why does Mercury have such an enormous iron core? Scientists have several competing explanations. One possibility is a gigantic collision early in Mercury's history. The young planet may once have possessed a much thicker rocky mantle. A massive impact could have blasted away a large portion of that outer material while leaving much of the dense iron core behind. Another possibility involves the conditions under which Mercury formed. Its unusual chemical composition contains surprisingly large amounts of volatile elements, suggesting that its history may have been more complicated than simply forming in the extremely hot environment close to the Sun. Some researchers have explored whether Mercury could have formed farther from the Sun and later migrated inward. But the idea that Mercury once occupied the region of Mars, or that it later collided with Earth and contributed material to the Moon, remains a speculative hypothesis rather than an established fact. There is no confirmed evidence that Mercury created our Moon. The Moon's formation is generally explained by a giant impact involving the young Earth and another planetary body, but identifying that impactor remains an active area of research. Mercury itself gives scientists another clue about its violent past. The planet is still contracting. Its enormous interior has been cooling for billions of years. As the interior loses heat, the planet slowly shrinks. The rocky surface responds by buckling, cracking, and forming enormous cliffs called lobate scarps. These structures can stretch for hundreds of kilometers across the surface. Messenger revealed far more of these features than earlier missions had been able to see, giving scientists a much clearer picture of Mercury's geological history. And the planet's interior is not completely dead. Mercury has a global magnetic field. It is weak compared with Earth's, but its existence is one of Mercury's greatest mysteries. A planet this small should have cooled much faster than Earth, yet some process inside Mercury is still generating a magnetic field. That field creates a miniature magnetosphere around the planet. When the solar wind crashes into Mercury's magnetic environment, magnetic reconnection can occur. These violent interactions can create enormous plasma structures and vortices that funnel energetic particles toward the surface. Those particles help knock atoms off Mercury's ground and feed its extremely thin exosphere. Mercury's exosphere is nothing like Earth's atmosphere. The particles are so sparse that they rarely collide with one another. Instead, individual atoms are continually released from the surface by sunlight, solar wind particles, and tiny meteoroid impacts. Sodium is one of the most noticeable components. And because sodium responds strongly to sunlight, Mercury develops a spectacular sodium tail that can extend millions of miles behind the planet. From Earth, specialized telescopes can sometimes detect this enormous stream of escaping material. Mercury is essentially losing pieces of its surface to space. Then there is its orbit. Mercury travels around the Sun on the most eccentric planetary orbit in our solar system. Its distance from the Sun changes dramatically during each revolution, and over extremely long periods, gravitational interactions can make its orbit chaotic. Computer simulations show that the inner solar system is not perfectly stable over billions of years. Mercury is particularly sensitive to gravitational disturbances, especially because of its position and orbital characteristics. That does not mean Mercury is about to crash into Earth. Any such event would be extraordinarily unlikely and, if it occurred at all, would be billions of years in the future. But it does reveal something important. Even the apparently orderly solar system can become chaotic when viewed across enormous stretches of time. And now Mercury is about to receive its most detailed examination yet. The BepiColombo mission, a joint project between the European Space Agency and the Japan Aerospace Exploration Agency, has spent years using planetary flybys to gradually alter its trajectory and lose enough orbital energy to reach Mercury. That is why getting to Mercury is so difficult. You might think reaching a planet close to the Sun should be easier than traveling toward the outer solar system. In reality, a spacecraft heading inward has to fight the Sun's enormous gravitational pull. It must shed orbital energy rather than simply accelerate toward its destination. BepiColombo has used a carefully planned sequence of flybys to accomplish this. Its mission consists of 2 spacecraft designed to study different aspects of Mercury. The European Mercury Planetary Orbiter will investigate the planet's surface, interior, gravity field, and magnetic environment, while Japan's MEO spacecraft is focused heavily on Mercury's magnetosphere and its interaction with the solar wind. Together, they are designed to transform our understanding of this mysterious planet. Scientists want to know how large Mercury's core really is, what its interior is made of, how its magnetic field is generated, how its surface evolved, and how its strange chemical composition came to exist. They will also investigate the polar regions and the deposits hidden inside permanently shadowed craters. And perhaps most importantly, BepiColombo could help determine which theories about Mercury's formation make the most sense. Was Mercury born close to the Sun? Did it migrate inward from somewhere farther away? Did massive collisions strip away much of its rocky exterior? Or did several different processes combine to create the planet we see today? The answers matter far beyond Mercury. Mercury is a natural laboratory for understanding how rocky planets form, how planetary interiors evolve, how magnetic fields survive, and how worlds change when they orbit close to their stars. It is also a reminder that distance from the Sun does not tell the whole story. The planet closest to the Sun has frozen water. A world with almost no atmosphere has a giant tail. A tiny rocky planet has a global magnetic field. Its enormous metal core is still cooling. Its surface is contracting. And its environment is constantly being reshaped by the solar wind. Mercury may look like a simple gray ball covered in craters. But underneath that appearance is a planet with a complicated history that we are only beginning to understand. And when BepiColombo finally begins its full science campaign, we may discover that some of our most basic assumptions about the smallest planet in the solar system were wrong. Because every time humanity gets a closer look at Mercury, the planet becomes less ordinary and far more mysterious.